at this session, we'll be talking about capabilities of photoelectric spectrometer, but in general about electrochemical measurements, because this instrument is designed for mostly electrochemical measurements, but it also can measure photovoltaic samples. All right. So we will divide this session in two parts. One will be kind of theoretical introduction to different aspects of measurements. And the second part will be using customer samples. Good morning, Professor Asaleh. I was waiting for you mostly because we will be measuring your samples during this session. So if you have them, at the end of the session, we can use them and do the measurements. This instrument is pretty simple. It delivers light to samples and can measure photocurrents produced by the light. And what we can do in 3 electrode mode, we can adjust the bias potential from -5 to 5 volts. And with the monochromator and the xenon light source here, we can deliver wavelengths from 200 nanometers to even to near infrared. This unit here is equipped only for up to 1100 nanometers. There is an improvement over all designs. We also can deliver light directly to the sample, white light or standardized white light. So you can use it as a solar simulator. So you place your sample inside, for example, by means of the cuvette. That is, you attach your sample here. You place it there, and you can measure both the response to monochromatic light and response to standardized white light or sunlight. Okay, I will move this a little bit. So the control parameters again are the bias potential, the light wavelength, and the timings. So how long the sample will be illuminated and how long it will stay in dark. You can adjust those. And what would you like to get out of those measurements? Basically, the instrument is designed to study samples' response to radiation, to light. Quantities that you can measure, those are external quantum efficiency. So this is IPCE. I will talk about it on one slide at the end. APCE, so this is full quantum efficiency, which is or internal quantum efficiency. Action maps, open circuit potentials, generally photocurrents and photovoltages. Okay, I already mentioned the parts, but I will still repeat that. So we have just light source and a monochromator that selects a certain wavelength. And here you don't see, this is an old version of the instrument, you don't see the sample chamber that is over here. But it is for the best because you can see another component of the system. And this is higher order sorting device because you have wavelengths coming of the monochromator that are multiple of the base wavelengths, and you would like to remove those higher harmonics. This is why filter wheel comes handy, because it has filters that remove unnecessary light. And you place your sample. If you measure low currents, you need to enclose it in some kind of Faraday cage or ambient light shield, because the distortion coming from stray electromagnetic fields will hamper your signal. And well, so this is light delivery system, and for measurements we use a potentialstat. All right. Then the potentialstat has the following capabilities. It is a small device. It can provide you with the bias potentials from -5 to 5 volts, and you can measure currents down to picoamperes. Even lower than this, but 1 picoampere is the number to keep in mind. But it is limited to 10 milliamps. For some applications, it may be not sufficient. And the application I have in mind here is codeposition. For codeposition, we have a potentialstat booster, which can attach to the potentialstat from the previous slide, can give you up to 1 ampere. And it also extends the potential range. Why we did this booster thing? For some time, we've been interested in those cold fusion experiments, and we just wanted to know why they didn't work. And we had our own ideas why. However, it is very hard to prepare the sample the way Fleischmann and Pons did in 1989. Many groups have failed in preparing those. And there was this guy, Paul, by the way, Professor Spack from San Diego, Naval Research Institute from the US, and he have found the way around to preparing samples in a reproducible manner. So instead of using palladium and deuterium and trying to pack as much deuterium atoms into the palladium crystalline network, he just co-deposited both at the same time, so he can control the load or the stoichiometry of the two components, and because of that he got reproducible results. So, however, the booster here is designed for co-deposition. If you will be interested in that, we have it. But I would like to keep this presentation or the workshop basic. So I would like to go back to show you how potentialstat really works. Because I got confused many times in my life about potentialstats. So I developed those pictures for myself mostly, but I'm gonna share them with you. If you have your cuvette, and this is a 3-electrode measurement, I will get back to why we use 3 electrodes, not 2 electrodes. But here are the 3 electrodes, a working electrode, which is your sample. It is submerged in some electrolyte, and you use counter electrode. So between those 2 electrodes, the current is flowing, and it's flowing through this ammeter, ampere meter. So it is measured here. And there is also additional electrode, which is reference electrode, which is connected to the voltmeter. And there are some subtleties in potentialstat operations, and I'm gonna delve into them right now. Suppose that you would like to measure just ordinary battery. So this is the battery, 1.5 volts. And suppose that you have additional meters. You have a voltmeter and you have the ampere meter here for current. We will be predicting what those meters should show. And they are connected in such a way that this red line denotes positive terminals. Okay, so plus is on the red. So in this setup, I have also used here this current that not the current, but the resistor that will limit my current from the battery. In this particular setup, it is not necessary because this guy has, for all our purposes, infinite internal resistance. So no current will flow, almost no current will flow through that circuit. All right, so let's do the prediction. As you may expect, the voltmeter will show 1.5 volts, while the ampere meter will show 0, because it is an open circuit. It is hanging in there. Okay, let's go. Now let's close the circuit. Now it is, you expected that. There is 0 volt, okay, and 75 microamps. Why it is 0 volt? Oh, of course, it is 0 volt because this circuit is closed, and this guy has 0 internal resistance. So from our knowledge of voltage, this point is exactly the same as this point, so there's no voltage difference. But now the current will be flowing. And this current, this value, we'll get to that in a while. However, how to understand those 0 volts? You have 1.5 volt here of the battery, and it did not disappear. It is still there. There is electromotive force giving that voltage here. But there is a resistor, and electrons are flowing in that direction. And there will be a voltage drop on that resistor that will be equal to the value, but opposite to the sign, to that voltage. So when you add up them together, you'll get 0 volt, no matter what resistor you put here. The value of this resistance, this is kilo ohms, just will tell you how much current you have in this, how large current will be, but it will not change this 0 volt value unless the resistance, even if resistance is infinite, it will show 0. All right, so where this number comes from? Yeah, this is a voltage, initial voltage. This is the resistance. When you divide the voltage by the resistance, you will get this value. So 20 case. I use this, though perhaps they are not the most convenient values to do calculations, but I did this experiment actually, and to show you, I will show you at the end the strange values. All right, now we are introducing Potentialstat to the system. Those voltmeters and ampere meters stay. So you can imagine that we are attaching working electrode terminal here, counter electrode over here, and reference at that point. This is not an open circuit anymore, because between CE and WE, there is a closed circuit inside the potentialstat. Okay, so there will be some current. But let's see what those currents will be. Okay, for this is exactly the same as on previous slide when we had the closed loop, and we had the potential of 0 volts there. which we understand where did it came from. So we also had a current of 75 microamperes. But now, what would be the readings of the current for the potentialstat? The reading will be minus 75 microamperes. And for set potential, it is not a reading really, it is our setting for setting on the potential 0 volt. This is not measured, this is set in the experiment. This is our control parameter. We will change it now to 1 volt. What would be the reading from all those meters? I will go first with the voltmeter. It shows also 1 volt, but it will show the current now of 25 microamps. Why is that? All right, we need to have 1 volt being kept between a reference electrode and a working electrode. This is where this voltmeter inside the potentialstat resides. It connects those 2 points. So we need to have 1 volt between this and this. And we have 1.5 volts. So we need to drop the 5 volts somehow. And we will drop it on this resistor. But we need to adjust current to do this. And the potentialstat will do just that. It will adjust the current. So when we need to drop this 0.5 volts, half a volt, on that resistor, we divide 0.5 by 20 Ks, by 20,000 ohms, and we will get this value. However, potentialstat shows the opposite sign. And I rarely agree with the conventions said in different fields, but especially in chemistry. But in this case, the chemists are on the right side of the force. And I will show later on why. But let's do one more exercise. Let's set minus 1 volt on the potentialstat, on the bias field. Now, the voltmeter will show also minus 1 volt. However, the current will be larger. And why is that? Because we want to have between those 2 points minus 1 volt, and we still have to drop this one, this voltage, and also in addition 1 more volt, because this is the difference between this setting and that what we have in our circuits. What it means, it is that we have 2.5 volt difference needed to be produced on that resistor. And if you divide 2.5 by 20 Ks, you will get that value. Still, the potentialstat shows the opposite sign here. And I will summarize that part, this introduction to potentialstats, that they don't just measure currents, they set the potential between 2 points, and they try to maintain this setting. Okay? If you say that often when we speak with users of our equipment and potentialstat in general, the beginners mix those things. They think that the potentialstat will be measuring for them this potential. No, it is a setting, and it adjusts the current, and it generates its own current to maintain the voltage set in the program. And this current is it's not natural to the sample. It is not generated in the sample, because we had the sample that consisted of just a battery and a resistor. And if you close the loop, it will do its own work. It will generate this 75 microamps of current. However, when you set up this with the potentialstat, and you do changes of the setting, the current will be different. So it doesn't come from the sample. It comes from the device. And this might be important for you if you want to consider nonlinear samples, because even if your sample has its internal electromotive force, so it produces, there is some reaction going on in the sample, you can still get currents going through that sample that are way different from its normal operation, and they may affect your sample. So you need to consider that potentialstat can harm your samples. I will show now on the same example how not to use it. And perhaps you will understand it better. So, is it really? No, this is this one. Now we have changed just the position of a reference electrode. We set it. It used to be on that side of the resistor. Now it is on that side. Okay, so we have the same building blocks, but the system will behave totally different. Why is that? Now we would like to keep up the voltage set in the potentialstat between this point and this point. So that means that we will have to somehow lose the difference between this voltage and the setting on the internal resistance of the battery alone. This guy doesn't play a role here anymore. It just limits the overall current, but it doesn't help us do a thing here. So what we'll get, those are strange results. The voltmeter, external one, not that in the potentialstat, will measure this voltage, and the current measured by an external amperemeter is also weird. So you may have the feeling now what's wrong, because what we have seen here, we have seen a limit of potentials that can be applied by potentialstat, actually, because the setting is 0 volt, okay, on this, between those 2 points. So we need to drop 1.5 volts somehow on the internal resistance, and this internal resistance is small. It is not 20 Ks. It is of order of 1 ohm or perhaps less. So that would mean that if it was 1 ohm and we wanted to lose this 1.5 volts, we would need to produce the current of 1 ampere. Our device cannot do this. It hits another limits because it cannot apply voltage high enough to the sample to even get close. So this value is completely wrong. It is our misdoing. Okay, and now another issue that we have run into a long time ago, but we realized that recently. When you have samples that have 2 contacts, then you can apply the potentialstat. Now this is a simplified version of a potentialstat. So those are internal meters in the potentialstat. And imagine that the sample has its internal serial resistance, the same as with this battery, and some electromotive force. So there is some reaction going on and produces this electromotive force. And we would like to find out what is this natural current generated by the sample when this circuit is closed. So when those 2 points are on the same potential. This means that the circuit is shorted at those 2 points, just out of the sample on one and the other side. And so we see the capability of the sample to generate some current. And of course, we know that what that current will be. It will be this electromotive force or this voltage maintained by the sample over this internal resistance. But of course, we assume that this doesn't change with the current flowing for now. In real life, this will drop as the current increases, but it is not important for us right now. But now we will go to the 3 electrode sample, because this is where strange things start to happen. So, if our sample is now surrounded by electrolyte, the electrolyte is on that side, then immediately when you submerge it in this liquid, it will develop a half-cell potential. It is denoted by this rectangle. And it will have also some sample electrolyte resistance additional. So there will be a barrier for current flow between the electrolyte and the sample. And this is the simplest thing we can do really with this setup. Then we'll have our counter electrode, let's say platinum piece of metal. It will also develop the same, I mean not the same, but similar, for the same reason, half-cell potential. So there will be potential between this electrode and the electrolyte, and there will be perhaps some additional resistance here. Because we don't want to consider that part of the circuit, we use the 3rd electrode. This is the reference electrode. And why does it help? Because if you can now imagine the current flowing through that circuit, so it goes through all of that, goes up, and goes back here. It doesn't go through that part because this guy has infinite internal resistance. So it prevents, for our purposes, no current going there. But if there is a current going, then if we measured, as before, the potential between CE and WE, we would have to account for the potential drop on the interface, platinum and electrolyte. And we don't want to, and this potential is tricky. It will depend, it will have all the abundance of effects coming from nonlinearities. It will depend on the history of the sample too. So we want to get rid of that. So we won't be maintaining potential between those 2 points, but between those 2 points. This potential is not really, but between those 2 points. Which potential we'll get to in a minute. This way, this half-cell potential will not affect the measurement of potential because there is no current going through that circuit. So there is no potential drop. Even if you have this half potential and no current, then nothing happens here. No influence. I mean, this won't be influenced. This reading will not be influenced by the current flowing through that circuit here. Okay. So this is why we use the 3rd electrode. And sometimes this is why we have this 3rd electrode, but it is why do we wet our sample in the electrolyte in the first place? Okay, you may ask yourself. Often you prepare samples that are that have just one contact. you have like ITO foil or FTO glass, and you put your sample on that glass, and that glass is just over here. So you have one contact of the sample, and you don't wanna spatter metal on the other side to change the properties of your sample. You just, but some people consider it lesser disturbance when you add electrolyte. It is not a small disturbance, but you can control it. You can control the concentration of ions in the electrolyte. You can control other properties. And because of that, you have many degrees of freedom into designing this contact. So this is one reason why you may want to wet your sample. Another reason is that you may want to study the reactions between something that is in electrolyte and your sample, and there's no other way around. So you use a 3-electrode system. But now, let's go back to our original problem. I would like to know what setting should I set here in this voltage, I mean on this voltmeter, in order to get this great short circuit current out of the sample between those 2 points, as it was in the 2-electrode setting. And this is a practical issue. Why is that? Tomorrow in the morning session, you will see EMPS, EMVS device that measures various aspects of lifetimes in your sample for minority charges or transport times through the sample. If you consider that there are carriers being generated on this side of the sample, then they would need to drift through the sample to the working electrode, or the other way around. It doesn't matter, but there will be drift there. However, if you want to find out what the drift is, what are the drift properties for those carriers inside the sample, then not the drift, sorry, diffusion. They diffuse. The drift I want to get rid of. So I don't want to put any external potential between those 2 points. I want to have drift 0, so I explore only diffusion, for example. And it turns out that you are out of luck. You would not be able to do this. And why is this? Let's now fall back a little bit and turn off our Potentialstat function and just measure open circuit potential. So we can use, in this Potentialstat, we can open the circuit, so we can break it somewhere here, and we'll be measuring. Actually, this voltmeter will be used for measuring potential, not just for keeping a certain setting of the potential. So VOCP, open circuit potential, will come from this measurement. So when there is no current flowing, what you'll have, what this OCP voltage will account for. It will account for this drop of potential and this drop of the potential. They have, and of course, for our electromotive force. Those guys come with the difference. This is a difference because when, depending on which way you go, you can adjust those pluses and minuses here. But the signs between them should be always. I mean, the sign should be with minus. So you need to subtract those 2 things, never to add. But so this is VOCP. So we know what is the voltage between this point and that point. But we are interested between W, E, and A in this point. Okay. So, and this is where something breaks down. what would be this short circuit potential that we need to set our potentialstat to in order to get the proper values? Okay, this will be the potential as before. And we should also account for the potential drop due to flowing current. And this current will flow now through this potential, through this resistor and this resistor. Those are two resistors in series. And you cannot separate between them. This is one thing. Another thing is neither you can separate those two guys, those two potential drops for OCP, because they are also in series here. So if you cannot separate them, you cannot devise a method for now just to have this potential of 0 between WE and point A. Okay, this is an inconvenience, but we did something drastic to our sample. We inserted it into the electrolyte, and this is why those additional potentials developed, and additional serial resistance. But okay, so we can think, let's do next best thing. Let's consider that we have a new sample and include those two guys into the sample. As it is, we have changed its properties, so perhaps those two quantities should now belong to the sample itself. So the next best thing is to have zero potential between point WE and B, all right? So let's do this. Actually, I already described what's here. So we have a, and this is what we'll get. In order to maintain 0 volt between those 2 points, we'll need to set this guy to cancel just this drop of potential, this half cell potential. Okay, so this is this, but this is even worse than before, precisely because this is a half cell potential. Its value depends on convention. We measure it with respect to like standard hydrogen electrode, or we can measure it with respect to anything. It should not enter our equations alone, always in pairs with something else and with negative sign. So we measure only differences between potentials, not this. So this can be anything. So we don't know what potential shall we set on the potentialstat to get 0 voltage between points WE and B. So even in this relaxed scenario, we are also unable to force our system to do that kind of measurement. So this is kind of I'm going ahead of myself a little bit. But some assumptions behind the measurements that we are doing every day are such that it is not a foolproof system, and it is not self-consistent even. However, if you do measure metals, there is no problem. Okay? It is only for semiconductors or things that can do interesting stuff in those setups. For metals, you will not have this. If you just put piece of platinum or whatever inside, you will not have this. Internal resistance will be lower than anything in the system, so you can neglect it. And when you have enough carriers in the electrolyte, you can neglect this part. You are good. So this is trying to use the tool developed for metallic samples to semiconductors that didn't transfer well. All right. I wish so far we had this closed. I mean, we had a system set up to measuring the currents, and for we now switch to another mode of operation. We will go to OCP, and why it is important. When I was a beginner in the field, I had trouble, and Dr. Bienkowski knows it very well. I had trouble understanding what OCP is good for. And now there will be an opportunity to tell what I learned. So now we disconnect this C electrode from the circuit. So the circuit is open. It is no longer being shorted by ampere meter. It is open. And we actually use our internal potentialstat, internal voltage meter as a meter, and it will be measuring voltages between RE and WE. Okay. So for that, in that case, everything agrees here. This current on an external meter agrees. I mean, it doesn't make sense because the circuit is open, but still, those two values will agree. And the voltages also agree. We are measuring this voltage. All right. Now, when we know what our OCP is, we can apply it to the cell. This is, we set the voltage of OCP on our potentialstat, so we want to maintain it. And now it is already connected, so we are back in the mode of current flowing, but the current doesn't flow here. It is still zero, okay? It will be still zero. And this is a good thing. So if we have this OCP, then we can start out with our sample with small currents. And for nonlinear samples that are history remembering, it might be a good point to start. You don't want to subject them to large currents or to spikes or anything, because they will remember it, and this will show in your results. So OCP is a good thing to start. And we will be, our software helps with that. We will show it in a second. You may want to set up, before you start your experiment, you may want to measure OCP and start measuring all the potentials set on the potentialstat from that value. This difference between set potential and the OCP value is called overpotential. And this overpotential is defined actually by this. This is the overpotential. Okay, so this is the set value minus the value that we got from OCP measurements. And you want to operate with this value because it will tell, if it is small, we know that the current is small going through the sample. Okay, this is basically, and perhaps we will be able to show it on our in our software. Yeah. Oh yeah. So we made it. It doesn't. We don't see the site. Can you somehow move the? Oh, there is the most important part is being cut off. Oh yeah, that's it. That's good. So when you do the measurement with the with this photoelectric spectrometer or with this Potentialstat, you can just select what you want to do. So you can go either with a reference electrode, and you will have ordinary potential here, or you can click on OCP, and you will have over potential. And this will also show what measured OCP was. Here is the time that you set for the initial OCP measurement. So the measuring procedure is the following. You don't shorten the circuit. You try not to advance any current through it. Before you do anything, you attach just the voltmeter inside this Potentialstat, which has infinite internal resistance, so no current will flow. It will measure the OCP, the open circuit potential. Then this software will plug it into the settings of your measurements, and with one click you can control already over potential. All right, back to the show, if we can. Actually, I need my my transparency. Yeah. Oh yeah. There's some glitch there. So let's summarize it as a good practice in measuring nonlinear samples and non-LTI samples or NLTV samples. So first, measure the OCP, then use over potential and track the history of what measurements you have performed on those samples, because they will remember the history. Another thing is that early on in our history, we had the Potentialstats that adjusted current measurement ranges automatically to the current encountered in the sample. And then people ask us to interpret the data. And the data was rarely reproducible, mainly because when you switch an internal circuit for the current range, it introduces those little spikes of current going through a sample. Other manufacturers also have this problem, but they hide it. They just don't show spikes. And we decided, no, we're gonna be open about it, and we will show to our customer what he's doing with his sample. And those spikes would be revealing that they may affect the sample, and it was out of control of a user. So then we decided not to allow the automatic range changing. So it is inconvenient at the first glance, but it turns out it saves you more time when you interpret the data than in our time also, when you have this automatic switch between ranges. So it is to your advantage, not to your trouble. We have those range switching features in other devices, like our light calibrators, because it doesn't matter there. But for samples measured with usually in your laboratory, it does. So we don't have, by default, we don't have this automatic range switching. All right. Now, since this is a conference about nonlinear phenomena, how can you check if your sample is linear with the photoelectric potentialstat? I mean, with the photoelectric spectrometer. So at least we can check two values. We can do IV characteristics. So we'll apply some voltage, and we'll sweep in time with this voltage, and we will measure the current generated through the sample. And we will be doing this experiment right now. Please switch. Okay. Whoa. Okay. So this is E versus I. E because electrochemists use this symbol for bias potential. And it is really that simple. If your sample is linear, it should show lines here. I mean, straight lines. Not many of them, but just if you have one sweep, this is actually produced a line. This is there's a linear sample inside. It is a capacitor and resistor in parallel. And you see this. So when you do the sweep, you see this straight light kind of over here, and certainly straight light down there. But there are some glitches here, and I wanted you to notice them. First of all, at the ends of the sweep, this is cyclic voltammetry. So we have the sweep that is going from 0 to some value here. And then we switch the speed of the change of the potential to negative, and we go back. And here we switch again, and we go back to 0. And there is something here. We will talk about this later. But when those switches happen, you have those nonlinear type of behavior, but it is not due to our input. I mean, it is not due to the sample's properties itself. It is due to our input. We have changed abruptly the input, and this is what our sample shows. So it is quite good linear. And now we can explain this part. Can we run another? Once more. Okay. Now we have exaggerated this initial spike here. And why is that? It seems like some glitch in the system, but it is not. It is just physics. Please go to my presentation. Yes. Thank you. We started our sweeps at some velocity, some volts per second. Okay. And then our sample initially was held at very different voltage than 0 voltage. I mean, that's the initial voltage. And in order to start the sweep, we needed to go from whatever sample potential was on to this initial starting value. And this great jump caused the spike going down. And this is described by this simple equation. It happens if your sample has a capacitance. So if there is a non-zero capacitance in your sample, then the change in the jump in this potential will cause you a spike of current. And this is exactly what happened. We had a change because we have some wild initial voltage, and we had to go to the voltage 0 because we started with 0. And apparently, this voltage, initial voltage was higher than the one we need to go to start our sweeps. So, higher? No, lower. It was lower because the spike was negative. So whenever you have this capacitance, you will have those spikes, and then don't worry about them. They do not mean that your sample is nonlinear. That means that something happened to your input. Okay. So we know that when this sweep speed changes, like from positive to negative, we have kind of nonlinear behavior. And when we don't control the initial voltage of the sample, it also may result in some spikes.
But usually we prepolarize the sample for 1 second at this potential, the starting potential, and we do not have the spikes.
That's great if you are aware of that. However, not everybody is. This is the thing. So I wanted to stress it here that this is IV characteristic is a good tool to find out whether your sample is linear with respect to those two parameters, I and V. All right, so much for the Potentialstat, but this device also produces light, and how much light does it produce, and in what range? This will give you an idea. So we have a xenon lamp as a light source, and it ranges from 200 nanometers to, we have it to 1100. And the reason why we cut off here is because the internal sensors mounted by default are based on silicon. And silicon gets transparent beyond that value, more or less. So our monochromator can pick up one of the wavelengths here and deliver it to your sample. But it cannot really adjust the amplitude of the light, I mean the intensity of the light, because xenon lamp is not great for adjusting the amplitude because it is unstable by its nature, and in order to have it working, you will need to maintain tight currents flowing through that through the arc. So it is not suitable for changing the light intensity. For that, we have simpler device that is called mini photoelectric spectrometer, and it uses LEDs to deliver light. But then you don't have this continuous sweep of frequencies. You have just discrete. Okay, now some people say instead of looking for an LED revolver or an LED source, I would open the slits for the monochromator and I will have more light, or I will close them if I want less light. This is doable, of course, and this device has automatic slits, so you can, older devices, they had manual slits, so you didn't really adjust that often those slits in your laboratory. People tend to set it onto one value and keep it forever. One reason is that the software could not record what was the setting for the slits. So in order to have reproducible results, yes, please.
Question about the same line.
Yes.
You need to correct for the output. You need to provide a correction for that.
So you need that I need to correct this. I heard the question, but I still don't understand this. I mean, this is not the spectrum of xenon lamp. It is a spectrum measured behind the monochromator, and all the characteristics of gratings inside, mirrors inside, are already included in this. Okay, in this value, it was measured outside of the monochromator already, so it is not. It's not a direct characteristic of the xenon lamp. I mentioned about the xenon lamp because I wanted to say that the range is basically determined by the xenon lamp and by the silicon detectors that we use. And if you cannot have light below that point from xenon lamp, monochromator will not produce it. All right. So you can open the slits and you will have more light, but you also will change the chromatic composition of the light coming to your sample. The wider the slits, the wider the spectral input to your sample will be. And typically for 1 millimeter slit openings, we use we use gratings that have 1200 grooves per millimeter, and that turns into the dispersion of this monochromator, which is around 4 nanometers per 1 millimeter of slit opening. So if you open the slit for 2 millimeters, you can expect this number to double. So it will be 8 nanometers of the half width of the light going to the sample. But why this light affects our sample at all? I would like you to see this toy model of a sample, because it is not well understood. Suppose that you have a semiconductor, and it is supposed to be sensitive to light somehow and produce photocurrent based on the light intensity that will be shined upon the semiconductor. So let's go back a little bit to energy diagrams. And those energy diagrams, they show a valence band over here and the conduction band over there. And we see that this level of electrons, some electrons are in the conductance band. So this is N-type semiconductor. And now you can do this Gedanken experiment. You can remove all the electrons from the sample altogether and put them back one by one. Okay? And we will be putting them back until we fill this valence band. So they will go from the lowest energy levels up to this point. And our sample will be accepting those electrons uniformly, meaning that those states described by the band here, they extend from one end of the sample to the other. So they are spread out evenly through the sample. But now we have reached this point, and we still have some electrons left, and we need to put them in anyway. However, there are no band anymore beyond this point, but we can have surface states. We forget about trap states and other things for now. And so when you can put those electrons, those are the only places. So they will be sitting on the surface until you fill up all the states up to the Fermi level. That means that the density of charges in the sample will not be uniform anymore. There will be negative charge accumulated on the surface. And it will repel all those electrons that are in, say, conduction band. They are movable from the surface. And you will have a positive or depleted region right at the surface. And this region is called space charge region. And this is a key player in sample's light sensitivity. So when you have light, we can do the following. We can take an electron from this place and move it to the conduction band if you have enough energy. It is a little skewed picture, but the question is it possible to do? Can you excite electron from this place and move it spatially to another place during the excitations? And the answer is no, you cannot do this. And there is a good explanation in physics. It is called Fermi's golden rule. And it basically says that the transition from one quantum state to another is ruled by such a matrix element. I mean, this is a Hamiltonian that describes this transition. And this is initial state and final state. And you can describe them as a wave function. So those two wave functions, they depend on position. And one, let's say, initial state is peaked around that point. The final state is peaked around that point. And this guy means basically that you have integral of the product of the red and the blue line. Okay, so this guy is proportional to this product, or integral of the product. But you see that when this has a significant value, the other is 0. When blue one has non-zero value, the red one is 0. So when you multiply them, you will get 0. So you will get 0 here. This probability is 0. It cannot happen. However, if those two wave functions coincide in space, as it is here, there is some non-zero overlap, and this will give you non-zero probability of transition. So the picture I have shown before, usually it has very low probability of happening. And the correct picture is this. We have straight lines in the energy diagrams. Okay, but the thing is that it goes both ways. This probability going from I to F, from initial to the final state, is symmetric if you go from F to I. So it will be given by the same matrix element. So when you have coinciding, when you excited your state, it is likely that it will go down because the probability of going down is high, because those two, you may think of wave functions, they coincide in space. So there's a good chance that they will they will recombine, as it is called. The excitations will be dumped, and the energy will be spread around the sample. Well, however, there is this savior here. This is the space charge region. And because of the potential here, there's a strong electric field in this charge void region. And this electric field can intervene when we excite this electron before it has a chance to go back to its initial state. Those two wave functions will be taken apart. I mean, the blue one and the red one, they will be shifted so they no longer overlap. And there is little chance for the recombination. So space charge region and the electric field in it prevents the recombination. Not prevents, but certainly helps creating those pairs and helps their survival. So we can have now, because of this electric field, because before they can go back to its initial state, they are moved apart, and this is where photocurrent comes from. The question is why metals are insensitive to light. Why we don't build solar cells out of metals? Have you ever thought about it? Why is that? Why we need those semiconductors? I don't know. I'm kidding. The first thought would be that they don't have space charge region because a good conductor cannot have those voids of charge of carriers. not the void of charge, void of free carriers. Okay, those carriers are those charges that can move freely, and other charges do not need to be carriers. They may be stuck to the place. And it is not actually the correct answer. The better answer is that the light does not enter the metal at all. If you have many carriers on the surface, they will adjust themselves to this electromagnetic wave coming, and they will reflect it back. So this is perhaps the key reason why metals are not that good in producing photocurrents. Okay, I told you yesterday that you cannot understand nonlinear samples if you don't understand a photodiode. And this is how to connect the photodiode to this instrument. So to get the correct conventional currents, it needs to be the photodiode needs to be inserted in this way. So this N-type semiconductor is facing the electrolyte, not the electrolyte, but the reference electrode, OCE electrode, and the working electrode is on the P side. So this symbol represents a photodiode, and it has this triangle here. This triangle shows the direction of current when this device is forward biased, meaning there is larger potential on WE than on RE, on CE. And understanding the photodiode is should start from perhaps this equivalent circuit. It is unlike equivalent circuits that you will get from impedance spectroscopy, because it has a nonlinear element in it. This nonlinear element is a diode. This is taken from All About Circuits. There is a great piece, a short article explaining how photodiode works, and I highly recommend it to you. And it explains in details, in reasonable detail, the meaning of the symbols. But here how it goes. So you have a PN junction that is represented here by ideal diode, and you have a current source that goes the opposite, in parallel, it goes opposite of this triangle. So it will be not the forward current, but it will be reverse current in the photodiode. So if you have light, this will be represented by this pump here that produces current. You also have some capacitance. This is this PN junction having separated plus and minus fixed charges that form some capacitance. So the junction there has a capacitance, and this capacitance depends on the voltage applied to the system. So if you apply some voltage here, this capacitance can change. And there is this shunt resistance or parallel resistance that you would like to have as big as possible, because it competes if you with your load. If you attach some load and you would like to do some work by this photocurrent to be done on the load, then this will shorten the circuit before, and some of the photocurrent will be diverted through that loop, which you may not want. And there is this resistance in series. This one, on the other hand, you would like to keep low. Why is that? Because you would like to have your photodiode linear with respect to light intensity. The photodiode is that great in building instruments because it gives more or less linear, I mean, not more or less, it's quite linear characteristics if it comes to current response to intensity of light that is shining upon the structure of the photodiode. So this is a great device. Linear, it's easy to calibrate, and some manufacturers, instead of measuring current produced by photodiode, measure voltage produced by the photodiode, which is a grave mistake. Because the voltage depends on the temperature of the structure of the diode. Current does not. But it shows also that you should measure really current produced by photodiode in order to assess how much light it experiences. So it is all good when this serial resistance is low. If it is high, there will be current flowing here, and there will be some voltage drop on that resistance, proportional to the current and proportional to that resistance. The plus will be here. That means then this plus also will be here, and that the current will go through that diode. And diode is nonlinear. So our detector loses its linearity, because if you have this resistor here. So photodiode. This is a PN junction, and it also has this light-sensitive part, which is this part void of carriers. It still has ions, positive on the N side and negative on the P side, but they are not movable. They are there for good, but there are no carriers. And because of that, there is also an electrostatic potential that prevents electrons from going here. However, this potential gives you electric field that will help separate any charges, any pairs of electron hole produced in that region. And this will generate photocurrent. By the way, this capacitance of the junction is more or less determined by the size of this space charge region, or this depletion region, as it is called. Okay. One more thing before we go to this hands-on part of our session. I would like you to remember that what those IPCE and APCE word abbreviations mean. IPCE is this incident photon to converted electrons ratio. So when we have light coming from your right, so this is incident light, and this is your sample. It can be reflected or it can be transmitted. And the third option, not mentioned here, it can be absorbed. The most important option, perhaps. However, what you really can do, you can only, you don't know what light will be absorbed. You can only measure incident, reflected, and transmitted. If you measure only incident light, which is the default setup for the spectrometer, you measure only IPCE, because those are number of electrons produced in photocurrent, and those are number of photons from incident light. If you have an extension, like this integrating sphere, or you have a calibrator and you can measure, if your sample transmits some light, you can measure transmitted light, then you can adjust this ratio by removing all reflected and all transmitted photons. So what is left is only absorbed photons. And this is APCE, absorbed photons to converted electrons. or internal quantum efficiency, or whatever name you have there. Quantum efficiency, just often it is just abbreviated to quantum efficiency. So the thing is that this number is greater than this one almost always. Unless they can be equal, but it is rare. So publication-wise, it is much better to show than this one. Okay. So this is the difference between those two values, and they all can be measured on the photoelectric spectrometer. I would like to stop now on that note, and we will be trying to measure samples from our guests here, so they can see how this system operates. And the rest of you, those who are not interested, they perhaps can get some refreshments around. But we can move closer here and see this instrument from close up, and we'll be applying some light and whatever to the samples. So thank you very much for this part, and we will continue doing measurements. I'll close now.